Earlier this year in 2018, NIST, the National Institute of Standards and Technology, released draft NISTIR 8202, which is their blockchain technology overview. I'm going to be breaking down this technology overview to explain what NIST feels blockchain is and how it can be used. Okay, so in a basic sense, blockchains are distributed, unchanging records of transactions. Once the transaction is published, it cannot be changed. So therefore, it is an immutable ledger. The first application for blockchain would be cryptocurrency. That's currently the application that we see out in the public. Right now, the biggest coin is Bitcoin, and there's others such as Ethereum, Ripple, and Litecoin. Blockchain in a cryptocurrency is used to store digital value. So NIST starts off in section 1 explaining the history of the blockchain. And blockchains are not actually new. In 1991, a similar situation using what was considered a primitive blockchain technology um, had cryptographic digital signatures that would be used to show the integrity of list documents. However, it wasn't until the pseudonym Satoshi Nakamoto wrote his paper, Bitcoin, a peer-to-peer electronic cash system, that blockchain was combined with other technologies to create a cryptocurrency. Now, other cryptocurrencies existed before Bitcoin. However, none of them really achieved widespread usage. The reason that Bitcoin achieved this widespread usage was because they were a peer-to-peer network. There was no central group controlling the currency, and therefore there was no single point of failure. In addition, this cryptocurrency eliminated the need for a bank to perform digital financial transactions and provides lower cost transactions. This system has a built-in maintenance program called mining. So basically there's miners, there's mining nodes. We're going to get a little bit more in depth with that in a bit, but mining rewards are given to users to help maintain the system. Only valid blocks are added to the blockchain, and they are validated through a consensus mechanism. This makes it very difficult to double spend, sending the same digital asset to more than one user. Bitcoin users are anonymous, but their accounts are not. All transaction history is freely available in the ledger. The system has complete transparency. The value is that a business can be conducted with untrusted and unknown users. The way that I think about this scenario is I think that blockchain, in the sense of a cryptocurrency like Bitcoin, is a trustless consensus network where you're coming to a consensus, but it does not involve the need for trusting each other. Okay, so now the next section in the NIST documentation explains the blockchain architecture, what's actually included in a blockchain. The first section is hashing. Hashing is a one-way function. So think of hashing as something like when you cook an egg, you can't go back. You're not going to go back to that egg that you cracked out of the eggshell. Once it's cooked, it's completely different. Now for a more technical description of what hashing is, I'm going to use an example in Python to show you using hashlib how to hash a string and get back a result. After the string is hashed, what you'll see is that the output is always a consistent length and it is a unique number. Okay, the SHA-256 algorithm is used by Bitcoin and it has no known collisions. So this means that it would be very difficult to figure out exactly what the hashes are and how to create the hashes. This is where Bitcoin gets its power from. So a little bit more in depth into SHA-256, there could be collisions because we're talking about an infinite number of possible strings compared with a finite number of identifiers. However, in the context of a blockchain system, it is highly unlikely that a collision would occur from a list of blockchain transactions. So it takes on average 2 to the 128th power to find a collision. Even one bit of change of one of the transactions would lead to a different hash. Therefore, the idea is that a list of transactions is blockchained and creates a SHA-256 hash as a digital fingerprint of those transactions. So in blockchain, a transaction is usually made up of an amount, inputs, which are assets that are going to be transferred, and outputs, recipients of the digital assets. Um, these transactions will also include a transaction hash. So basically, taking all the data in the transaction and hashing it into a hash value, such as the SHA-256 hash value that we looked at before. So blockchain uses asymmetric key cryptography, which means that there's two keys, a public key, which can be exposed to the public without compromising security, and a private key, which is kept secret. Users sign transactions with the private key, and then public keys will verify signatures signed by the users who are using the private key to sign. In addition, public keys are used to derive multiple addresses for a single user. So your public key is not actually your address, and we're going to go into that in a minute, but the public key can be used to derive multiple addresses. This ensures that the correct user is the one sending the value, and no one besides the user with the private key can sign a transaction on his digital value. Okay, so in terms of blockchain addresses, addresses are given to each user. So one user can have multiple addresses, but each address is assigned digital assets. So to spend an address, you must prove possession of the address with your private key. Once you sign a transaction with your private key, the transaction is then verified by the public key. Now, the next thing that NIST goes into is private key security. When you store your private keys, public keys, addresses, and the amounts of the assets that the addresses have, um, this is called, this is basically a wallet software. So a wallet software, again, would include the private keys, public keys, addresses, and the amount of assets for each of the addresses. Okay, so in the next section, we look at private key security. Private keys are generated using secure random functions and cannot be recovered if lost. Private key security is extremely important. If someone steals a private key, they can completely control all associated digital assets. Since a blockchain is immutable, once the user's public key plus some additional data is hashed, hold on a second. So private key security is extremely important. Most private keys are stored directly in the wallet. So the wallet would include the private key, the public key, the addresses, and the amount of assets that that address has. Private keys are generated using secure random functions and cannot be recovered if lost. Private key security is extremely important. If someone steals a private key, they can completely control all associated digital assets. Since a blockchain is immutable, once this is stolen, you cannot recover. The user's public key plus some additional data is hashed to create an address. Addresses are used to send and receive digital assets. There can be to and from addresses. Users can generate as many public-private key pairs as they wish, which would give them multiple addresses. This gives users a bit more pseudo anonymity. Public addresses are not secret and are sometimes used to generate a QR code for ease of use. The user's public key plus some additional data is hashed to create an address. Addresses are used to send and receive digital assets. There can be to and from addresses. Users can generate as many public-private key pairs as they wish, which would give them multiple addresses. This gives users a bit more pseudo anonymity. Public addresses are not secret and are sometimes used to generate a QR code for ease of use. Now let's go into a little more detail about what the ledger is. So blockchain in its simplest form is a peer-to-peer distributed ledger, an immutable ledger. So a ledger is a collection of transactions. For example, even just writing transactions on a pen and paper or putting transactions into a central database is considered a ledger. The shortfalls of a central database is that the data can be lost or destroyed in one single place. So you must trust that the owner is backing it up. Also, the integrity of the data is all up to the owner. If the owner decides to allow corrupted data or corrupt the data themselves, there's only one person that's in control of that. So basically, in a central database, you must trust all the transactions and the user or the owner who is validating the data before storing it. Also, there could be missing data, and you have to trust that the owner is going to keep track of any type of missing data. The transaction data can also be altered, and the owner is responsible for making sure that that data is not altered. However, in a peer-to-peer blockchain ledger, all ledger data is copied to every full node. So everyone has a complete copy of every transaction. So new transactions are submitted to a node. This node will then alert the rest of the network that a new transaction has arrived. This pending transaction. This transaction will eventually be included in a block if deemed valid. All data is stored in blocks, and a full copy of the data is sent to all users. Okay, the next part that NIST covers in this document is the anatomy of a block. So, what is a block? Users submit candidate transactions by sending to nodes that are participating in the blockchain. These candidates are propagated to everyone in the network, where wait in queue is a transaction pool until they are validated and added to the block by a mining node. So, what is a block? Users submit candidate transactions by sending to nodes that are participated in the blockchain. So, let's go over what a block is. Users submit candidate transactions by sending to nodes that are participating in the blockchain. These candidates are propagated to everyone in the network, where they wait in queue in a transaction pool until they are validated and added to a block by a mining node. Mining nodes are specific nodes that maintain the blockchain by publishing new blocks. Transactions are part of the block being published. Transaction validity is done by checking the provider's ins have the sufficient funds in the account and have been cryptographically signed with their private key. Blocks that have any invalid transactions are rejected. Created blocks are hashed. This helps protect the block from change because all nodes have a copy of this block's hash. Therefore, even a minor change would result in a completely different hash value. So next, we will look at the actual breakdown of what is included in a block. So the block includes the block number, which is also known as the block height, the current block header hash, the size of the block, a list of transactions included within the block, and the block header. Now, the block header includes its own subset of data. It has a hash of the previous block header, a timestamp, the nonce, which is a solution to the hash puzzle when mining, which we will go over in depth in a later part of this video, and the Merkle root hash. And again, the Merkle root hash will break down as to what exactly that is as well. Okay, so section 3 of the NIST documentation talks about how a blockchain is expanded through the addition of new blocks. This process is more commonly known as mining. So blockchains are maintained through the consensus of mining nodes. Okay, so there's different types of nodes. There's a lightweight node, which is a partial portion of the blockchain. These would pass their data onto full nodes. This would include IoT devices and smartphones. The next type of node is the full node, and this is running the full blockchain software. It's ensuring that new blocks are valid, blocks are correct format, have been signed, have enough funds, and the hashing is correct. And also, it's passing transactions to other nodes. So now the most important type of node is the next node that we're going to talk about, and that's the mining node. Now the mining node runs the full software of the blockchain, but also has to have a computer with resources associated with that mining software. So a computer with a good hash rate, that would be, so that they can participate in solving the hash puzzles. This would be for a proof of work mining node. We're going to go over in a bit the proof of work versus proof of stake. But for right now, a mining node is primarily associated with proof of work mining. Each node contains a copy of the entire blockchain. Each can submit potential transactions to other nodes, which then get propagated throughout the network. All nodes can submit transactions. These transactions are sent to unspent transactions pool, which is where it waits to be included in blocks. Blocks can be created using a combination of older transactions that were waiting for some time and newer transactions that are offered a higher payment. This is when the mining node structures a block with all the data except for the nonce. So what's happening here is the mining nodes are actually preparing the blocks in the exact block structure that is required for that particular blockchain, but they're leaving the nonce empty because, as we'll see later, the nonce is important for the proof of work mining. To actually create the next block and add it to the blockchain, this will require some sacrifice on the part of the miner. So that's why you're going to need a computer that has a high hash rate. So in proof of work mining, you're expending time and effort, and you're trying to find the nonce to solve the hash puzzle. In proof of stake mining, you are actually putting up a portion of your account balance as a stake that you could potentially lose for the privilege to mint the next block. So a little bit more detail about proof of work mining. A proof of work miner tries to combine different values until they solve the hash puzzle. Now, these different values are numbers. These numbers are known as the nonce. So the nonce, when it believes that a miner has found a solution, is included in the block, and the hash value is computed and put into the block as well. Then the block is sent out to the other nodes for verification. If it is accepted, it is continued to be sent out throughout the network to the other nodes. So section 4, it is looking at the need for consensus models to resolve conflicts among the blockchain. So many mining nodes compete to solve the hash puzzle for the right to chain the next block. These miners only know each other by public addresses. So right now, again, what's talked about in the NIST documentation is that it's primarily the proof of work mining. These miners are motivated only by financial gain and not the health of the network. This is because the winning miner receives a reward for solving the hash puzzle. So these miners are all competing with each other, trying to build up the best computer with the highest hashing power that they possibly can. So back when Bitcoin first started, as Bitcoin as an example of a proof of work mining protocol, it began on regular laptops, and people were able to, compete in this mining hash puzzle. And then what happened was it went to, desktops, more powerful computers. After a while, the CPU was not powerful enough, so things started to switch to GPU mining. So it would require you to have a intense graphics card. The older graphics cards were perfectly fine in the beginning. After a while, you had to buy the more powerful graphics card until you needed the best graphics card that there possibly was to be able to mine. After the graphics cards ran out, people experimented with like programmable gate arrays and stuff like that. But then eventually the ASICs were released, which are application-specific interface cards specifically for SHA-256 algorithm to perform the hash puzzle in Bitcoin. As you can see, this process, this evolution of mining nodes is not only expensive to buy the equipment, but it's also very expensive to use electricity to power this equipment. Okay, so when a user signs up for a blockchain, they are agreeing upon the initial state of the system. Now, this state of the system is recorded in the Genesis block. So basically, the structure of the Genesis block is what these users are agreeing upon. And they're saying that, okay, we have this Genesis block and we agreed upon it. But now after this, we want to create blocks that can chain to this block. So there are no questions about the validity of the network because users are agreeing on the Genesis block and then they can verify every other block. Also, all blocks are linked with hashes except for the Genesis block, which is typically recorded with zeros in the previous block hash. So users agree to the consensus method. If two people solve the blockchain at the same time, the one with the longest chain is always considered the right chain, or at least in most blockchains, the longest chain is considered the right chain. So the Bitcoin client software handles all of the consensus, so there is no need to have a third party. Okay, so the Bitcoin software or the blockchain software handles all of the consensus, so there is no need to have a third party. Every user verifies the system integrity themselves. Temporary disagreements may happen, but even if malicious users try to take over the blockchain, users must eventually come to a consensus. Therefore, blockchain is a trustless consensus engine. So the proof of work consensus model is a computationally expensive hash puzzle. It's easy to check and it's hard to solve. So this puzzle involves having a number that's of less than a certain size and making small changes to this number, which is known as the nonce, until you get the appropriate hash value of the block header. So once you find this appropriate value, you set your block up in the correct structure, and you would pass that on to another node, and that other node will begin to see if this is valid or not. And if it is, then that will pass it on to more nodes. So that's how the proof of work is propagated. So these puzzles, these hashing puzzles, can be modified for difficulty, which they're modified based on how many people are trying to solve the puzzle. If more people are trying to solve the puzzle, the hash rate is higher. So basically, for example, Bitcoin adjusts difficulty every 2 weeks to keep new block creation to an average of 10 minutes. So the puzzle is equal every time. It's like a fresh start. Everyone has the same advantage in solving the puzzle. There is no advantage for having solved previous puzzles. You're on an equal playing field every time that a new block is announced and people start trying to solve these puzzles. So the way that you can have a better chance of solving the puzzle is by increasing your hardware's hashing power. This will only help you solve the current puzzle, though. It doesn't help you past the current puzzle because the nonce input space is reduced with each try. When users receive a proposed winning block, they are incentivized to pass the block on because this winning block will be sent to other nodes. Therefore, if you aren't keeping up with the longest chain, you could end up on a shorter chain. Shorter chains would be rejected in case of discrepancies, and therefore that is why the longest chain is always the best chain in the blockchain proof of work system. So if you ended up on a shorter chain and you were trying to put all this work into the shorter chain, you would be mining for nothing and you'd be losing money. So you always want to be on the longest chain. So that's why you pass these blocks as soon as the answers come in. Once a node solves the puzzle and sends out the solution to the other nodes, recipient blocks check the work and then add the block to their copy of the blockchain. This makes it easy for a new block to quickly propagate across the network. Verification is simple. You only need one hash to make sure everything is correct. So basically, just checking the hash on the block will tell you if the nonce was correct or not. Okay, proof of work is excellent when you have all users who do not know each other and have no trust relationship. This system makes it very difficult to cheat and create false transactions. However, energy consumption is a major problem of the proof of work blockchain. It is said that the Bitcoin network uses just as much energy for its proof of work mining protocol as the country of Ireland. And also by 2020, this energy consumption may increase to the amount that Denmark uses. So right now, Bitcoin, an example of a blockchain, is extremely difficult for one computer or even one ASICs to solve. So the solution is mining pools. Mining pools divide the nonces among the nodes. So they give you a couple nonces to try, and basically they try to cover all of the different nonces. When mining as a group, you can achieve more consistent rewards as the rewards are divided among the participants dependent on the contributed hash power. So when you're in a mining pool, whatever you put in, you should receive a reward for the amount of hashing power you're using. Okay, so now let's look at the proof of stake. So proof of stake is based on the philosophy that the more stake a user has in the system, the less likely he is going to want to do anything that will decrease the value of his stake. An example would be hacking the system. So this user not only doesn't want the system to get hacked, he doesn't want to be the one hacking the system, or at least for it to be known that the system was hacked, because if a system gets hacked, the cryptocurrency value will decrease and that user will have less money. So proof of stake uses the account balance of the user and some other variables sometimes, such as the age of the coin of the user, to determine who will create the next block. The more stake a user has, the more likely they will produce new blocks. In chain-based proof of stake, users' stake is compared to the blockchain, and although the block creator selector is somewhat random, it is weighted based on the percentage of stake that you have in the blockchain. So a user that has 2% of the total blockchain stake will become the next block creator 2% of the time, while a user with 48% would be chosen as the block creator 48% of the time. Now, a lot of systems also incorporate other variables to prevent the same miner from staking over and over again. So an example of this would be Peercoin. Peercoin uses something called coin age, and the coin age racks up for your coins in your balance, and then you can stake that coin. But after that coin is staked, that coin age will reset to 0 for that particular coin. Now you still may have other coins that you can also stake, and then they'll lose coin age. But once that coin age resets to 0, then it has to build up coinage again to be eligible for staking. Another example of a proof of stake system is Byzantine fault tolerant proof of stake. In this system, several miners are selected as proof of stake miners, and the miners have several rounds of voting to determine who will create the next block. This is a much more democratic system where it gives a voice to all of the um, POS miners who are chosen. Ultimately, proof of stake is a low power alternative to proof of work. Some blockchains do not have rewards or mining for blocks at all, or even new block creation. In fact, in some blockchains, all the blocks have already been created and distributed among users. Um, an example of a blockchain that is completely created already is the popular Ripple cryptocurrency. Now, in proof of work, we said that energy consumption was the big issue. Um, Now, the issue, according to NIST, in proof of stake is that the rich generally can always stake and increase their account balances. Um, Therefore, they will just keep increasing and getting richer. However, for even a rich person to control an entire popular blockchain um, would be very expensive. Now, just a little bit of additional information to control the entire blockchain, you would need greater than 50% of the blockchain, which is usually way too expensive. So, a less popular method of consensus is round robin consensus. This is used more for private blockchains. It's where nodes take turns creating the blocks. And this would require trust relationships within a private blockchain. So, you'd have to trust all of the mining nodes. A level of randomness is added to the nodes so that if one node is down, it doesn't completely destroy the network. It will go to another node. This is a low energy solution because there's no proof of work hash puzzle to compute. However, this could not work on the public facing internet. Um, Not only is there no complex cryptographic proofs, malicious actors can keep adding new nodes until they control most of the new block creation, which completely brings the integrity of this type of consensus and ultimately the blockchain that runs this type of consensus into question. However, in a completely private network where you would need credentials to log into the blockchain, it may be possible to use this type of round robin consensus. So there's different ways that conflicts on the ledger are solved. Um, Again, because there's no central authority, ledger conflicts do happen. Sometimes two blocks coming in at the same time, either because of network latency or they just came in at the exact same time, need to be corrected quickly for the blockchain to continue to grow. When two blocks are propagated and begin growing, it is usually waited on for the next block to see who is the longest chain. When the longest chain is determined, the transactions that did not make it into the longest chain are returned to the unspent transaction pool and will be included in the future blocks. Section 5 of this NIST documentation introduces the concept of forking. In a distributed system, blockchain updates to the software or implementation of the blockchain are called forks. There are hard forks and soft forks. Soft forks do not prevent users from using old software. However, the majority of the nodes need to accept the change for the fork to be successful. Soft fork examples would be when Bitcoin used part of the code that was previously given for a no operation command and instead changed it so that it would be a check lock time verify operation. And this new operation would be used for a time released escrow. So basically, users with the old software would run the no operation command still, but users with the new software would have the ability to use the new functionality. However, both pieces of software were able to um, continue to exist together on the same blockchain. However, a hard fork is different. A hard fork is when everyone needs to completely switch over to the new system or they will not be allowed to use the new blockchain. Users on different hard forks cannot transact with one another. Forks may be useful for users to prevent cybersecurity issues. If a flaw in the software would allow for a hack, users can abandon the existing blockchain system and move to a hard forked new blockchain. An example of a hard fork is when Bitcoin forked into Bitcoin Cash. Now, what happened there was discrepancies among the developers of uh, when to increase the block size for the transactions. So Bitcoin Cash was a group of miners who promised that they could create a faster coin than Bitcoin right away. So they allowed more transactions per block, which ultimately gives you a faster version of Bitcoin. Right now, both coins exist. There's Bitcoin and Bitcoin Cash. And basically, anyone who owned Bitcoin before the fork now owns that same amount of Bitcoin Cash as well. So they own Bitcoin and Bitcoin Cash if they owned before the fork. So one cybersecurity issue with the future of blockchain is that quantum computers um, may be able to hack cryptocurrencies in the future. And now this is documented in this NIST documentation. So um, basically, if cryptographic changes were needed, this would require a hard fork. So RSA, for example, relies on integer factorization. And then there's DSA and Diffie-Hellman, which rely on discrete logarithms. Both are susceptible to quantum computing. Merkle trees, which is what we went over before with the SHA-256 hashing, are less susceptible, but there is ways to weaken them with quantum computing. Now, switching out the cryptography on a blockchain is not easy. So it would require a hard fork, but then you're going to run into a lot of specific issues. For example, if SHA-256, which is the Bitcoin um, hashing algorithm, were to be compromised, the SHA-256 is part of is basically the ASICs hardware. So this is an application that specifically hashes SHA-256. It's a hardware application specific um, card that's going to basically hash this SHA-256. Now, if the SHA-256 became compromised, everyone who bought all of this expensive equipment would have to switch to a different type of ASICs and they would completely lose their entire investment. Also, there could be a potential gap in the mining if everyone has to abandon at the same time. Um, so that would be a terrible situation for SHA-256 to become compromised without any warning. Okay, so Section 6 of the NIST documentation defines and discusses smart contracts. Now, Bitcoin, it does not necessarily take advantage of smart contracts the same way that Ethereum does. So now, what Ethereum promotes itself as is almost a decentralized mainframe. So this this type of blockchain can have code and data deployed directly on the blockchain. So transactions can send data to public functions on the blockchain. The user data is then executed within the function to perform a service. The code on the blockchain is unchanging, therefore it can be used as a trusted third-party service that is much more complex than a simple transaction. Smart contracts can be financial or non-financial. For example, they could forward money to a different account, or they could do something like generate random trustworthy numbers. Um, Now that's what the NIST authors are claiming that they did. They actually had built a smart contract that generates trustworthy random numbers. So mining blockchains that include smart contracts would require all miners to execute smart contract code while mining new blocks. So to entice the miners to do this, there could be additional fees associated with mining smart contracts because it's more than just a simple transaction. So it would require more um, computing power. There is a limit in the execution time on all smart contracts. Now, the reason for this is a cybersecurity reason. Um, what could happen is a malicious user could attempt a denial of service attack against the mining node who is mining that smart contract. So it would basically eat all the resources in an infinite loop. So that's why each of these smart contracts includes a limit in their execution time. So section 7 of the NIST documentation is going to look at different types of permission models within blockchain. So there's permissioned and permissionless. Now your standard Bitcoin is permissionless. However, there are some blockchains that are for internal users only that are permissioned. These blockchains are like the equivalent of a private intranet. Um, this can be used within multiple organizations that have some level of trust sharing between one another. Permission blockchains are used. Um, so there's different reasons for using a permission versus a permissionless blockchain. Standard blockchains like Bitcoin are permissionless. However, there are some blockchains that are for internal users only. These blockchains are like the equivalent of a private intranet. This can be used with multiple organizations that have some level of trust sharing between one another. Permission blockchains are using freely read-only access, and only a few of the users will have write access. Um, Now, there's also versions of a permission blockchain where only some people can read the data. So, most of the time, everyone has read only in this type of a permission blockchain, but sometimes you may just want it so that only some people can read and some people can write. So, very interesting. In the next section, NIST is saying that um, there are security applications for permission blockchains. Um, they do say that blockchain is usually an improvement over the current system, and it must be considered carefully to ensure security. So you have to think about certain things before you go ahead and implement a blockchain. Um, One of them is, does the blockchain allow for granular permissions that provide enough separation? For example, the blockchain may have standard author, auditor, and a validator, but do you need other access control levels? For example, do you need a another type of a user, such as an editor or something like that? Um, so that would be one thing that could be a deal breaker for you actually purchasing a permission blockchain, or creating a permission blockchain with a team of developers. Also, if a user is given admin rights, sometimes these rights can't be revoked because a blockchain is immutable. Um, Therefore, you have to look in to make sure that everything you're doing fits into this immutable model. Okay, another security concern when implementing a permission blockchain is that because of the level of consensus um, is different than in a public blockchain, what's going to happen is it's less computationally expensive for these permissioned blockchains to do the mining. So, do you have the trust in the mining node? If you don't have trust in these nodes can perform malicious activity. If you trust all the users, then all the users can mine. If not, use dedicated mining nodes where you've specifically chosen users that are trustworthy. Um, Another deal with mining nodes is, can you detect malicious mining nodes that are sending fraudulent transactions to themselves? So you should make sure that on your network and in your infrastructure, you have a system in place that watches for this type of activity. So again, back to immutability. Immutability is also a problem because of malicious activity. So when malicious activity is performed, it cannot be undone easily. You would have to rewrite published blocks at the point of where the malicious act was detected, and then fork the blockchain, which would have to get approval of all the mining nodes. Now, this is in a public system. However, in a permission system, it's much easier to do this. So um, there there are benefits in the intranet based blockchains where you can um, get the approval of everyone that you need to rewrite this, because you're not dealing with a group of untrusted users on the public internet. So some good uses based on this NIST documentation for permission blockchain um, are going to be the banking industry. Now, in the banking industry, it suggested that a private ledger with Byzantine Paxos mining protocol be used. Um, There are some problems with this, as banks would not be anonymous, and any mistake would be hard to fix because of the immutability of the blockchain. So basically, what that would be is these banks would share a private, permissioned blockchain like what we discussed. Um, they could share data between themselves, and they could even have a sort of a proof of stake system where they're voting on who should mine the next block onto of this data, or it could just be done through the round robin. Um, the next industry that NIST is looking at for permissioned blockchains is supply chain. This is great for tracking physical goods. For example, from farm to table, you could track a pack of strawberries. This would help encourage transparency and trust between vendor and customer. Another option would be that you can monitor supplier actions so that a warehouse could avoid overstocking. And then the last industry that they look at for permissioned blockchains is healthcare and insurance. So basically, when you have insurance agencies, many things are happening behind the scenes. Anytime a claim is made, um, multiple transactions happen between the doctors, the nurses, the insurance agencies. All of this could be written to the blockchain, and instead of being in different systems, it could all be pulled from the same system, which would also include your benefits and your coverage. Okay, so now permissionless systems are what we know on the public internet. All of these cryptocurrencies are right now permissionless systems. So permissionless systems can only work if rewards are associated with maintaining the blockchain. So that's why digital currency, is a very good application of blockchain, because it creates that financial incentive for miners to maintain the blockchain in an effort to get rich. So it's basically a greed engine. Um, do you need to figure out if you need a permissionless blockchain for something that you're thinking about implementing? You need to think about a couple different questions. Uh, Especially, you have to consider the data. Now, can the data that you're going to be putting into this blockchain be public facing data? Um, Also, do you need a full transaction history? Because these permissionless systems are keeping track of everything in an immutable ledger. The next thing would be, are you okay with hacking attempts on your data? And are you sure that all of the data that you need is going to come from valid sources across the internet? Or is there a different way for you to obtain these sources of data? So also, can the data be immutable? So if you're thinking about standard software development, what we say is um, it's CRUD. It's create, read, update, and delete functions uh, for an application. Now, in blockchain, all you have is create and read. You don't have the update and delete abilities. So that's going to be your question when you're architecting a system and determining whether you're going to go with a permissionless blockchain, a permissioned blockchain, or no blockchain at all. Um, okay, so another idea that you have to think about is, how fast do you need this system to be? If we're talking about a system that has to have instant data transactions, Um, Blockchain is most likely not going to be something that you would want to use because um, it has to go through the whole mining protocol consensus, and usually that takes a while. So the blockchain is slow compared to a centralized application. Okay, so now let's look at some use cases for the permissionless blockchain. There's trusted timestamping, which is basically if you have a file such as a signed document, an image, or that an event occurred, you can basically write that into into a the blockchain. Now, the way that you would probably want to write that into the blockchain is you could hash that information and then write that into the blockchain. Um, and then you can prove that that same exact information is equivalent to that hash. Um, Now, the benefit of this is that these blockchains are public record and they are immutable and they cannot be faked. Okay, the next use case that NIST looks at is the energy industry. The energy industry can benefit from blockchain with machine to machine transactions for tracing transactions on a smart grid. Issuance and spending of emission certifications has also traditionally been a problem area with double spending as a common concern. This can be solved through the blockchain. Um, Another outside the box idea would be that energy usage can be recorded into a blockchain, and you can trade renewable energy on a market if you can record it into a blockchain and give it a value. So in section 8 of the NIST documentation, um, they take a look at the different types of cryptocurrencies that are currently out there and blockchains. There are some blockchains that are not cryptocurrencies. Now, the first blockchain that they look at is Bitcoin, um, which is basically the pioneer of blockchain. And Bitcoin is basically a system that uses proof of work mining. It has a SHA-256 hashing algorithm. There's a block released every 10 minutes, and people are trying to solve this hash puzzle. Now, when you do solve the hash puzzle, the mining node would initially get 50 bitcoins for each block that was chained, right? So every time that they minted the next block or added the block to the blockchain, they would get 50 bitcoins. But after a certain amount of blocks, that number gets reduced. Um, for example, the reward for mining a block was 12.5 bitcoins in July 2016. So ultimately, there will be 21 million bitcoins produced. Okay, another important aspect of Bitcoin is that it does have a transaction language called script. This is not a Turing complete language, so it does not have full functionality of some other programming languages. Uh, However, for the most part, Bitcoin transactions just use a simple template to transfer funds from one person to the other. So the next blockchain is also a cryptocurrency. It's the fork of Bitcoin that I mentioned before. It's called Bitcoin Cash. Now, what had happened was 80 to 90% of the Bitcoin miners, meaning they vote using their computing power, they voted for the segregated witness. Um, which basically it splits transactions into two segments: transactional data and signature data. So this makes it possible to reduce the amount of data being verified in each block. Some people did not like this idea and felt that they had a better solution, closer to maybe Satoshi's paper, even, or that's what they claimed. And they forked to another coin called Bitcoin Cash. So technically, um, Bitcoin is actually the fork, and Bitcoin Cash is the original blockchain. But if you had your coins in Bitcoin before the fork, you have both. You would have both the equivalent amount of Bitcoin Cash as Bitcoin. Okay, so the next blockchain is also a cryptocurrency. It's called Litecoin. Litecoin is basically a faster version of Bitcoin. It has many similarities to Bitcoin. It uses a lot of the Bitcoin source code. Um, it already has segregated witness implemented into it, and it can it actually uses a different hashing algorithm called the script algorithm. There's also 84 million total Litecoins, or there will be 84 million total Litecoins when the last coin is mined. Now, Litecoin is not meant to be something that replaces Bitcoin. It's supposed to be a complement to Bitcoin with higher transaction volumes, um, instead of being a replacement to Bitcoin, which is supposed to be something that will store um, value long term, almost like a vault. Okay, so the next blockchain that's mentioned is somewhat of a cryptocurrency. Um, it was actually said today by the U.S. federal government that Ethereum is not a security. Um, so Ethereum is technically a currency, also like Bitcoin, and what this is it is a machine, basically a peer-to-peer machine that allows for smart contracts to exist on the blockchain and be accessed by users. So these smart contracts can act as basically trusted parts of an agreement, so that you can set up smart contracts for all different sorts of functions. Now, Ethereum also has a concept called gas, where it uses ether, um, and basically every transaction consumes this type of gas. The gas limit per smart contract is 3 million gas to prevent computationally expensive programs from being submitted to Ethereum mining nodes. Okay, so again, the submission of a transaction to Ethereum contract causes a program to run in parallel on the mining node's computer. The resulting state of the contract is stored on the blockchain by the user that publishes the next block. Okay, so Ethereum Classic um, was created when Ethereum hard forked after the DAO hack. So there was a hack that had happened after a certain type of a smart contract was added to Ethereum. Um, and the attackers drained $50 million worth of Ethereum. So the Ethereum Foundation created a hard fork to move the stolen funds back to where they were before the attack took place. But a lot of people felt that that was not something that should have been done because the blockchain should have remained unchanged. So they created Ethereum Classic, and it's basically very similar to the standard Ethereum. It's just because of that attack. Okay, Dash is a proof of stake cryptocurrency that was built around providing faster transactions than Bitcoin. So it uses a concept known as master nodes, um, where people can actually set up these master nodes for 1000 Dash collateral. And it's very expensive to control more than 50% of this network. Now, these master nodes are basically the miners. Dash uses a hashing algorithm called X11. This consists of 11 SHA-3 contestant algorithms, which actually include Blake, JH, Kekak, and Skyne. Okay, so the reason that Dash does this is because they want it to be very difficult to create ASICs um, for mining their currency. Okay, another cryptocurrency listed in the NIST documentation is Ripple. Um, the goal of Ripple is to build on Bitcoin and offer different types of payment systems. Now, Ripple is at a fixed supply of 100 billion, and half of them have been put into escrow where they're not available for circulation. Um, Ripple clients do not need to download the entire blockchain, making it easy for them to do to join the network. Additionally, there are no rewards for running servers because each transaction costs a small amount of Ripple, and this Ripple is similar to Ethereum gas. Therefore, no nodes or mining pools are needed. So basically, 1,000th of a cent from each transaction is destroyed. So the next blockchain that's listed is a blockchain that's called Hyperledger. The Hyperledger project is supported and hosted by the Linux Foundation. The goal is to create an enterprise-grade open source distributed ledger. There are several projects within Hyperledger. So the first project within Hyperledger is Hyperledger Fabric. This is a permissioned blockchain that can run smart contracts. And it has been contributed to by Hyperledger project by Digital Asset and IBM. Hyperledger Sawtooth is another Hyperledger product. And in this system, it uses proof of elapsed time as the consensus protocol. Every participant requests a wait time from a hardware enclave, which distributes wait times randomly. Whichever participant is awarded the shortest time creates the next block in the chain. So it's almost a form of random. Okay. The next Hyperledger version is Hyperledger Iroha, which is meant for institutions to share data and manage identity. Okay, another Hyperledger is Hyperledger Burrow, which is a permissioned smart contract enabled blockchain. It accepts Ethereum based smart contract code. And the last Hyperledger product listed in this NIST documentation is Hyperledger Indy. This is an independent identity platform providing for trust transactions and accountability. It supports user controlled exchanges of verifiable claims and identifying information, as well as a revocation model. Okay, so um, NIST then says that for the most part, there's a tendency to overhype and overuse new technologies, and they feel that this may be the case for blockchain. So definitely take into consideration your data and many other factors, such as can this live in an immutable environment before going through the hassle of implementing a blockchain, which is pretty difficult to implement properly. Um, so in the next section, 9.1, NIST is basically trying to explain that the phrase "no one controls a blockchain" actually should be "no one controls with whom and when you can perform transactions within the rules of the blockchain system." So the software developers actually do control the blockchain, and they can fork the blockchain as necessary, but no one is actually controlling a permissionless blockchain in terms of who's able to submit transactions and perform transactions and mine it. So another important aspect of blockchain security is making sure that the financial rewards of staying an honest user are better than being a malicious user. Now, if a malicious user um, is getting enough power in the system to cause damage, they can really destroy a blockchain. Okay, so that's basically the greater than 50% attack, and that can happen mostly in a proof of work with enough hashing power, but also if in proof of stake someone owned greater than 50%. But basically, once these malicious actors have obtained what they need, they can ignore transactions, they can alter transactions, and they can refuse to transmit blocks to other nodes, which will definitely disrupt the blockchain. The way to combat the malicious users right now is just forking. So um, if a some sort of an issue is discovered, then you'd have to fork the blockchain. So sometimes you may be able to uh, gain back the money lost in a hack, such as what happened with Ethereum. But other times this may not be the case, and you may move forward without a fork. And you know, people have to accept that that's the type of cryptocurrency that they own. So something else that NIST is trying to make clear is that when people are saying that a blockchain can act as a trusted third party, that's also a little bit misleading, um, because you do have to have some trust in different aspects of the blockchain. For example, you need to have trust in the cryptographic technologies such as SHA-256. You have to have trust in the software developers that they did a good job of producing a bug-free software, and you have to have trust that most of the users of the blockchain are not colluding, because if they did gain 50% of the block creation power, they can get around the blockchain rules by basically controlling the blockchain during the time that they have greater than 50%. Another issue would be that you have to have trust that the nodes are accepting and processing the transaction fairly. So resource usage is also a concern from NIST. Bitcoin's blockchain data is over 100 gigabytes in size as of January 2018, and it's going to continue to grow um, for as long as Bitcoin exists. Uh, Another issue, as we talked about before, is that it uses a lot of electricity per proof of work mining. So blockchains have limits on the amount of data that can be stored and are not to be general storage media. So you're not going to put um, massive amounts of data in your blockchain. You're going to put maybe hashes of files or something like that. You know, you're not going to want to use this like a regular database to store everything. If you do need to store data, you can store this data elsewhere and have pointers or references to that data that can be stored off chain. Okay, so another issue that NIST is describing is that users must manage their own private keys, meaning that if one is lost, uh, that's it. You lost your private key. You can't access the funds. Now, when you use a centralized system to store your keys, you're again back to this central point of failure, like any other type of centralized system. So it's probably not a good idea to upload your private keys to any cloud solution or to keep your currency on an exchange, because if the centralized exchange gets hacked and your private keys are stolen, then there's nothing you can do to get that back if those pieces of data or values within the blockchain are stolen using those private keys. Another thing that NIST wants you to know is that even though blockchain uses public-private key infrastructure, it doesn't support identity. The reason for the keys are to sign the transactions, but um, that's just signing the transactions and verifying the transactions. It does not support identity. The only way to link back a private key to an actual person um, in a blockchain such as Bitcoin would be something outside of the blockchain. So it does not support identity management in that way. However, there are possible ways to use blockchains for identity management that is not necessarily something that blockchain can handle as a standalone identity management system. So NIST wraps up this document by saying that um, blockchains are in widespread usage right now, and that blockchains have the power to disrupt many industries. So you should definitely investigate blockchain to see whether your organization should start using it or not.